welcome back to another video. We have our first snow here. Yeah, so in this video we'll check out the overcurrent protection board. We saw that it had a bit high input resistance, so it was 0.2 volts drop over just that one. Sorry for the wind. And then I'm going to try 3 other MOSFETs and see if those works better. And then they're supposedly a lot better, the power MOSFETs. And then I will try the overcurrent protection feature if there's time to the end of the video. Okay, bye bye.
Hello and welcome back to another video, and in this video I'm just going to talk about the OCP version of the C64 Saver. I have sort of given up on the Savers, however there's some activity on GitHub on some of my issues there, and yeah, so I guess I will try to figure out what was wrong with the OCP version. OCP is the overcurrent protection version. This issue is from May, and I found out there was a problem with the C64 Saver 2 choice of power MOSFET. So the power MOSFET is this chip here, up there. So this is the one cutting the power. And then you have some circuitry to control the gate of that one. Here it also has a current monitor resistor or shunt resistor up in the corner there. So we found out that the IRF5305, it was having a lot of voltage over it when it was on. So I measured 200 millivolts, and that's a lot when you think of it. 0.2 volt is a lot when you don't have that much margin. Like you're adding something in between your computer and your power supply. RDS on is it's not this figure anyway. It's a bit higher, and it was promising, but however what I didn't see was that it was measured for VGS at 10 volts. And that's what this video is about. I'm going to try 3 chips, and also the start of this video will be about trying this board to get up and working, because I don't get anything on the output. It's not conducting anything, so let's have a look. And also the other reason why I have started this is because there are people chiming in, Everlasting Engineering, and he has done some measurements himself. I have a couple of boards I made. This is OCP V0.1 with modifications. So this was supposed to be 0.2, but it had a mistake. But it looks pretty cool. It's from Osh Park, but this is from Aisler in Europe, so I wanted to try some European manufacturers. And Aisler, I'm not sponsored by either of these two, Osh Park and Aisler, but this is the OCP V0.2. It has the fixes that I forgot here, so let's have a look. And it's not working. I have moved all components from this board, which was OCP 01, over to this one, and it looks okay, but it's not working. So let's have a look. If you look up on the screen, we see the saver. It's the same circuit as we used to as before, and on the right side it's the same circuit. On the left side you have the current monitor circuit, and it's optional, so you can decide yourself if you want to connect it up. Now I don't see anything on the output, and this diode is not connected. That means it doesn't affect the circuit at all on the right side. So yeah, so let's have a look. I've connected negative probe or common input of the meter. I connected to ground here, up here, sorry, and then we have voltage here. So it's actually on now. I have the limit on 1.5, so we have on there. So, and also it's not an overvolted situation. So let's see. See here, this is the input. It's of course showing 5 volt, and the other side of the shunt showing 5 volts. So the shunt is making a voltage drop that can be read back from the current monitor over there. And then in on the MOSFET over here, it's 5 volt. I can show you on the diagram if you want. And then the output is 0, so we can measure the output here as well. It's 0, which is unfortunate. So let's have a look at the schematic and see what we can do. At the schematic, you can see the first thing you measure was voltage coming in here, and we can do it on the full screen. And then we had the shunt up here, and we saw that it was the same voltage on both sides. The voltage will change if there is a current going through it. Then you will get a voltage drop, of course. However, we didn't see anything on the output of this Q3 here, which is the RF5305. This is the chip that we are going to change later when this is starting to work though. But first we need to get it up and working. So this is basically the output of the saver. So let's fault find. So we have checked this thing on the top, the voltage on the top, the voltage in. So the next thing I want to try is see if this voltage divider is working. So I'm clicking highlight wires up here. The reason for that is then we get a highlight in the PCB editor here. So we see it's just below this one. So let's have a look. So that means we need to measure the second resistor from left under the thing over above there. So under the power MOSFET, which is on top. So let's see. As you see, it's exactly there, and you can see the meter shows 2.3 volts, which looks good. And just to make sure that this voltage divider is working, it's supposed to go up to 2.5, because that's where this, if you look at the screen again, this is where the sensing TL431 perfect diode thing, which I can't remember the name of yet. It's sort of a voltage monitor. It will trip at 2.5 volts. So we have the trip on at around 5.40 something. Let's try it again, and then it's supposed to be 2.5 there. So let's try it again. Alright, so that's 2.5. That's perfect. So that part of the circuit is working. So let's go beyond U2. Let's see if U2 has what's on the output of U2. So that means here. And we expect that to be hold on, we have to turn power down. Voltage back to 5.03 again. So let's just double check what we had on the voltage divider, 2.3. So that means this current monitor is supposed to be off, I believe. That means the voltage over it should be high. So let's see what the voltage is over it. And then we look at the screen again, we can see we have to measure. Well, we can measure here, there's several places, but we just go to the left of the resistor that we was at just recently, and it's 4 volts. That's a bit strange. I think it's supposed to be closer to 5, so something is pulling it down. Let's have a look at the schematic again. Well, yeah, it's actually something down here pulling it down. But it's not supposed to pull it more than, like, I'd say 10% or something. The next thing we want to check then, we are expecting the output to be high. That means we're expecting the gate to be low, but it's not. So that means this one over voltage string is supposed to be low. That means we need at least 0.7, 0.9 of that Q2. So let's see what we have there. Alright, so let's have a look. So they say we are going to measure, let's measure over that diode down there, which I haven't populated anyway. And it's 0.93. So that should be more than enough to turn on that, supposed to turn on that NPN transistor. So, but it's not turning on. So as you can see in the diagram, we have 0.9 over here, but the output is still high. So then you gotta ask, do you have enough current going in here? I'm pretty sure something got wrong with Q2, so I believe I will just swap it out. So I think that will be my best bet. There you go. So this is Q2. It's next to the LEDs down there. I'm just going to swap out this one. I think that will be good. And I will also measure some resistance over here just to make sure. So yeah, so looking through my filament boxes, and I guess I found this old purple thing here. I think it was Oshpark back in the day. So anyway, so we found the U1. So that's TL431. We found Q2, which is basically the RF5305, but I didn't find Q2 or Q1, so I guess I will have to look at more boxes. Moments later, I found this one, and I guess that's exactly what I need. Alright, so not going to turn this into a soldering video or anything. So what I do is that I pick it up, I solder one pad only, then I put the tip of the iron a little bit in on the pad, but not far, such that I can move this one into the iron. But since I'm getting old, I have to take off my glasses first. And then also, what we like to do is bring in the lights as well, because I'm also getting old. Well, my eyes are getting really old. But yeah, I still see stuff. So when I solder SMD, so that's good. So that's it. No, it's not. Okay, maybe it's not enough solder on this pin. There, drop it. So now it's on that pin, so let's make it even closer. Let's have a look. For soldering the rest, it's pretty straightforward. You have an overlarge tip, like everyone talking about. You have this tiny chip, right? Wow. Yeah, but solder finds its way by itself, so that's my tip for the day. Alright, so that's it. So I'll have to inspect it more closely just to be sure. So this is where the camera is actually quite nice. So hold on. Yeah, that looks good on this side. Could be better maybe. Voltage in is 5 volt. Out of the gate is now also 5 volt. Now it's actually working. That's great. Now let's see if you can switch off if the voltage gets too high. 0.4 there you go. Yeah, so that's working, and it's going to be further down when it goes on again. So now we're going to add the load. So this is my setup. Yeah, the voltage saver. I connected one of the wires from another saver that I just cannibalized the connector there. We have the old load board. It's currently on. Just have it on like this. 5.1 volts, I think. And I'm going to turn off the load, and I'm just going to read out the numbers, and I will look at my own video later and figure out the voltage drop. So I will assume that all current is going through here. Let's turn it on. Load is on. 0.9.5 or 95, and the drop is 218 millivolts, 217. Turning off the load. VGS, which is negative, therefore we need to have positive on positive and negative on negative. Turning on the load. I'm gonna measure it over here actually. And it's 4.9, that's great. Okay. So I guess the next thing to do now, well, we saw there's about an ampere and there's 280 milliamperes. And in my head that's about 200 milliohms of resistance when this one is on. That's a lot. We have to get that value down Or else the voltage presented at the Commodore 64 will be 0.2 volt less. So, okay, so I have 3 candidates here, and one of them is IPD 042 P03. I'm not sure what that means. Well, it's a MOSFET. Yeah, 40 volt MOSFET. That's the voltage of the source and drain, I believe. Also a P-channel SQD50 P03. Then, whatever. And then we have TJ40 SO4. So let's start with that one. Yeah, just got it off without the hot air gun actually. Right, so it's soldered in. It's the TJ40 SO4 and 3L. Let's see how that performs. Turning on the power. Let's turn it on, and just turning on the load now. Oh, yeah, that's working. Getting it out of... Yeah, that's also working. So, yeah, so this is working. I'm not going to test it that thoroughly, as you can see. You can see it cuts the power. For, let's see, 0.98 or 99. Alright, so let's remember that. Turning on the load. We have 11 millivolts. What the heck? And then we have... Do we have... Oh, 4.9, that's good. Okay, turning off the load. Wow! I mean, wow! That's really something, isn't it? Let's put it back in the bag. Let's try the 2 other ones as well. Let's see how this goes. I rented 340C. It's a bit high, but you need a lot of heat anyway. So when it starts to bubble, it's ready. Let's see. There you can see it already is melting. Might actually ruin this one, but that's okay for this experiment. So that's it. It's a lot of talk and very little action, so as per usual. There you go, it melted into the board table. So yeah, it's just gonna let it cool down and then put it back into the bag and then bring out the other one. Okay, next up it's the SQD50 P0307. Already showed you this, but people like soldering, so instead of replacing the solder every time, I guess it's okay just to reuse. Is what I like to do, is just put more flux on it. It's not like this is very dirty or anything, so we need to just hold it down. Okay, let's put it in there. There you go. Probably not the way you're supposed to do it, but it works very, like, it did work very well. So now I just have to, like this, there. Oh yeah, this is working. 5 seconds, but there it is. Let's have an inspection. Because my eyes are so old, I will just use the camera. So this is soldered, yes. Okay, everything's connected up. Let's have a quick look at the... Okay, let's turn this one down a bit. Let's have a quick look here. There is no current. Actually, that's because I've turned off the load. So let's turn on the load. Okay, let's bring it down into normal. Ah, that looks good. And it's doing what it's supposed to. Yeah, there. We have 0.99. Let's say that. There you go. 5.186. Let's turn on the load.
5.01. So that's what we're going to remember. Let's see, just for fun, let's see the shunt. Doesn't show very much, it's about 10 millivolts. Probably enough. Turning off the load again. Let's see VDS. Turning on the load. Measuring VDS. Or VGS, sorry. Looks very good. And then the drop over the thing. Doesn't want to measure. 8 millivolts. Wow! It was 11 before, so. And it's still 0.99. So. Amperes. Very good. So this one is even better. So that was the, let's see, it was the SQD 50P03. Okay, so this is the last one. So this one is Infineon IPD 042P03L3. See, 4 millivolts. It's as if it's not true. Like, take it away, yeah. Get back, 4 millivolts. That's great. And as you can see, 0.99 amperes. Turning off the load. Really happy about that. So that was actually the best one. And so this one, Infineon. But I will update the BOMs, bill of materials, and I will stop using the IRF 5305. So yeah, that was a bad design choice. And then I put the project away, like in 2020. Didn't pay so much notice to all of this, but I started noticing that the whole saver was having a lot of voltage drop over it, so, and it was getting a little bit hot as well. So now this one is supposed to be very cold under operation. Yeah, maybe it's a part 2 for this overcurrent thing. Actually, I found I found this one, BAT41. Is that the one I need? I think it's BAT42, but yeah, there you go. BAT41. Okay, so I have it. Alright, so before I end the video, let's try the overcurrent protection. So let's try. I have it 5.19. This is about 1 amperes. And overcurrents. I don't know what I have configured this to do. So it's supposed to be orange. And I guess it's kind of orange. Maybe not so much on the camera. Yeah, but that's cool. So if I turn, you can see that the current there is just 1 milliamp. So that's just the LED. Turning everything off, turning it on again. Now it's actually working. So now it's not tripping. So something is weird. Okay, let's try it again. There you go, it trips. So I need to have a look at this, and probably it's just missing some capacitors. Capacitors here I used to stabilize, like here. This is the sensing input, so this is the output of the comparison. Shunt resistor up there, and then you have measurement of that. That's the output of the measurement, so the difference there will be an output voltage, which is then divided, and yeah, you see the ground at the bottom there. And then we also have a capacitor, and I'm pretty sure I have that. Let's see, turn the light again. Yeah, C3 is not connected. Okay, put a 100 nanofarad capacitor in there. Let's have another go. Turning on power, turning on the load. Look at that. I can see if I can do it really fast. Yahoo! So this is working now. So if you want to see, we have load 0.99.
So yeah, so I have slowed down that input thing. So yeah, that's good. That problem solved. So I just selected 100 nanofarad. I haven't decided yet what to do about that. And you can actually take these two values and you get an RC constant. I also would like to see if it works. I'm not sure what kind of trip point I have, but I'm just going to manipulate here, and I think these are in series actually. So if they are in series, I can short circuit some of them. Yeah, it's a Max 4373 TSA. And looking at the data sheet, we see TSA, it's 20 gain. Yes, it should have been 50 or 100, I think, because now that we've changed from 40 to 10 milliohms up here in the shunt, the voltage isn't that great anymore. It's actually 4 times less. So this could be an issue actually. This is something I've changed now. 40 milliohms. So that was what I had. Maybe I should put it back. I mean, because I have the wrong circuit now. I can of course change everything. Maybe I don't know actually, because this one will give 4 times the sense voltage. Right, so I put in the 40 millivolts shunt resistor there. It's not that looking that great, but yeah, it's soldered. So yeah, we got an overcurrent as fast as I turn this off, so I'm gonna turn it on again. Now I'm gonna try turn it off and on, and it's still yeah, it's still on here. So it was on while I was turning this one on, then it's also cutting. So I don't film everything, but I have this thing from China. It has all 0603. It has some capacitors as well as resistors. Nice to have. And figure out that you know, this load is only 1.1 amperes or something. So let's turn it off and on. Now I can turn on and off the load, no problem. But if you look closely, it's kind of jumping about a bit. So if you do this up to 2 amperes, then it triggers. So yeah, so what's happening here is that this capacitor, which is this is the dummy load. The dummy load also has a capacitance. The C64 has capacitance. So I'm emulating that, and it's actually tripping here. So it could be that this 100 nanofarad wasn't great enough. Maybe I need 1 microfarad. Maybe I should calculate that now. But I know that the current into such a capacitor is quite large. So yeah, that's one thing. Or we can figure if we could just raise the trigger point, because I don't know what it is. So that will be for another time. I've looked at this before. I actually need a current source or current. Now I have the electronic load. It's a bit messy right now, so but I only use it to trip the overcurrent. So let's turn it on. It's a do-it-yourself thing, and you can already see it has been cut, but it doesn't really cut. It just indicates, because I had to change the circuit. So and this has a function that I can take 100 milliamps at a time, or I can click it and then I can go 10 milliamps at a time, or 5, I think.